Hello everyone, this is Terrence Hall, and this is a quick video description of the Lab03 programmable stopwatch on the Digital Basis 3 board for my CPE 3020 course. The purpose of this lab is to create a VHDL component that provides a basic stopwatch functionality. The user will enter a binary value using the 7 onboard switches. Once the user presses the start-stop button, the two rightmost 7-segment displays will start at 0 and count up 1-second increments until it reaches the converted integer value. Once that point is reached, the 16 onboard LEDs will display a victory pattern until the start-stop button is pressed, or if the reset button is pressed, or if the user inputs a higher binary value. Looking more into the component file, we have our ports imported here from the wrapper previously. We have the clock imported that reads at 100 megahertz per second. It's capable of going up to 450 megahertz, but it defaults as 100 megahertz. And we have our start stop count button configured to be the center button. And then we have a reset button configured to be the down button on the board. We have our constants here that convert the binary signals inputted from the switches and converts them for the 7-segment driver so it can display the correct values. Since we want the clock to go up in 1-second increments, we have our constant here that sends a pulse of 1 hertz, and that's essentially our synchronous base that allows the components to work in synchronous with each other's. We have our constants here. These are for our state machines for the complex victory pattern. And then we have our signals for our bottom components. And we'll get into more of those a little bit later. We have our 7-segment driver imported here. That part of the component is provided to us by the professor, and that's displayed here. And then we have a LED driver, which is our state machine that we created that does the complex victory pattern. And here's the port map. And like I said in the beginning, the clock will start at 0, so we have the digits here. 3 being the rightmost and the 2 being the second rightmost, so it starts off at 0, 0. And then our port maps for our LED drivers. Our first block, we have a binary to integer converter that essentially gets the inputs from the switches, with the 0 being the rightmost switch, and then the 6th one being the 7th from the right, and it gets the binary value and converts that and converts it into the in target value. Our BCD converter, it takes that binary value that's inputted and separates those essentially. So we're able to separate the 1s and 10s, so the 10s will be displayed on the second rightmost LED display, or 7-segment display, and the rightmost being the 1-digit display. And we have our constant here that displays which value it needs to display depending on which case it is. We have our detect press here, and since it's a synchronous input, we have to have it, we have a nested if statement that has a wait for release value, so that once the wait for release is not active after the start count is initiated, the start stop count will essentially start the process at the end of the rising edge for the clock that allows for the synchronous increase. And here's the timer as well. The timer is a synchronous input, and that's relative to the 1 hertz counter we have, so it'll increase in 1 hertz increments. Here's our failsafe here that it prevents the counter from going over 100, and it can't go over 100 because we're using just 2 LED displays. It wouldn't be able to recognize that. So once it hits 99, it'll just display zeros, and we'll go into the victory display pattern. Here's our mode logic component that initiates going from the timer mode to the LED mode. The timer mode is initiated when the start-stop count is active, and will reset once the reset is active. And we'll go to the LED mode once the end target reaches the current time. And since those are both integers, we're able to use this operation to set to see if those values are equal to each other. Like I said before, this is the timer display driver. This is provided to us by the professor, and essentially the logic for the driver itself. And then here is our state machine driver, and how we have our components laid out, how our victory display pattern will be displayed. It'll have a value coming in from the rightmost, and that value will skip to 0 and go to 1 all the way until it reaches across the entire board. And then once it gets to that these last two patterns, these last two states will alternate, and we'll see that later on in the code. And this also is synchronous, so it also has its own internal clock, so it'll change at a 4 hertz process. So it'll be a little bit faster than the segment driver we had previously. And this essentially is the logic here. Starts off as a blank LED, and then once it reaches the LED control, which is switching from timer control to LED, it'll go to the next state, and the next state from the blank state is load 1, and so on and so forth until it reaches the final 2 states. And it'll alternate from full 1 and 2 from here. Here's our blink rate for our synchronous clock, and like I said previously, this one works at a 4 hertz time cycle, so it'll be a little bit faster than the 7 segment display as they were incrementing there. And I guess we'll start looking at the test bench in just 1 second. Here's a quick video description of our wrapper for our programmable stopwatch component. We have our ports listed out here, the clock, switches, segments, anodes, center buttons, down buttons, and LEDs. We have our clock set as the default value, which is 100 megahertz per second, and we're using the 7 rightmost switches, or 0 through 6, and we're using the 7 segment display, 0 through 6, and we imported the anodes. And we're using our center button as the start-stop counter and the down button as the resets. And since we're using all 16 LEDs, we imported it as 0 through 15. And now I'll be handing the video off to Michael to continue talking about the test bench.
So for the test bench, we wanted to show full functionality of our component, as well as show a special few end cases. Now you can't show every single possibility here, but we want to show some extreme cases, as well as counting from 0 to 99 and showing just the basic functionalities as well. So we decided to just go ahead and lay out a couple tests we wanted to perform and expected outputs here. We'll dive more into those as we actually go through the simulation, but that's how this entire test bench is structured. We have 8 different conditions that we want to test to, and we'll go through those with the simulation. So inside here we declare our constant, our signals, and our component down here. We port map to our component with the same names. We've got our clock declaration in here. We use 100 megahertz frequency, just like that. Now it is important to notice, for all the other parts of this test bench, time is scaled to 1,000 times. So when we go through the simulation, 1 millisecond will be equivalent to 1 second. So we've got our reset driver here, and as I was talking about earlier, we initialized the value of reset to 0 as well. As I was talking about earlier, we basically just took each one of these steps and use that to map each one of our inputs, user inputs. So, if reset's not being used, we just wait through that. That's how the first steps are. But for instance, like the third step here, reset's pressed for 5 milliseconds, and then we wait for another 10. So reset's active for 5, and for the last 10, it's not active. And so we go through that. For the reset, we have a button driver for our start-stop button. So we can see that. And we have, whenever we want to start-stop, for an arbitrary time, I just chose 50 microseconds, so like 50 milliseconds, as if the user just tapped the button. But long enough to where the clock can still recognize it. A human's never going to be able to outspeed a 100 megahertz clock, so long enough to where the clock can recognize it. But just like the last one, we initialize it, and then we go through each of the values here. So we can see when we want to press the button, we do so. And then our switch driver, we're just simulating different values the user can put in for the switches. So we initialize it to 0 for the first case and put our wait statements in and initialize it to different values for each time we need to. So now we can get into the simulation. So for our simulation, let me go ahead and zoom to fit, and then I might bring this back and zoom in a little bit so we can see it a little better. Something like that should be good for now. So our first condition is to set the switches to 0, wait 10 milliseconds, and the expected output is to be double zeros on the 7 segs, and LEDs are blank. So as we can see here, I just picked a random time inside of here, but we don't see any signal changes inside of this first 10 milliseconds. We see on the 7 segs, our 1s and 10s are both 0. And then we got nothing on the LEDs for the entire time. And then our next step, step 2, switch is set to 0, start button pressed, wait 20 milliseconds. Our expected output is still zeros on the 7 segments, but victory pattern on the LEDs. And I'll zoom in a little bit more so we can see these first couple steps, which are a little harder to see without it. But we've got right here, we can still see 1s and 10s digit is constant throughout the entire time. But if I expand the LED pattern, and also we can see the start stop button right there, we can see our victory pattern play. So we see the rightmost light up, then we go up, and then we alternate between those two. That should do it for that state. So let me zoom back out. So that goes for 20 milliseconds, and we can see the victory pattern stops upon 30 milliseconds, which is our step 3, which is reset button is pressed for 5 milliseconds, and then we wait for another 10 milliseconds. So we expect the solid 0 on our 7 segment, so only the rightmost will be displaying that. It means only the rightmost anode will be active, or in this case not active because of the logic of that. And then we expect the LED pattern to stop immediately, which we can see it does. And our LEDs will go back to regular double zero. So let's just confirm that real quick. I might have to zoom in a little bit on this one. If we go to anodes, we can see for this it is set to just E, or aka only the right one is active, and our 1's digit is 0, so that's good, and we see our LEDs are 0 for that entirety. Alright, so now we can look at step 4, which occurs at 45 milliseconds. So now we set the switches to 10, and start is pressed, we wait 4 milliseconds, stop is pressed, wait 5 milliseconds, and then reset is pressed for 7 milliseconds, and we wait another 10 milliseconds. So our expected output is we want to see climb from 0 to 4 on our 7 segment display, and then we want to see it stop at the 4 millisecond part, and then for another 5 millisecond it just hold that 4 value, and then we want to see a solid 0 as we did with the reset on the last one, and then 0, double 0 again to show the reset worked. So we can see our start stop enable pulse right here, and we can see our ones digit, our tens digit is constant 0 for this. Our ones digit goes from 0, 1, 2, 3, 4, and that's when we have another pulse come in, and it holds that value for the prescribed amount of time. And then we have a reset press here, so we can see our solid 0 and our anodes at the proper state. So E meaning only the rightmost is on there. And then upon that reset, we go back down to double 0. Fantastic. Alright, so the next state starts at 71 milliseconds. I'll read that out for us. Our switches will be set to 9. Our start will be pressed. We wait 4 milliseconds. Stop is pressed. Wait 5 milliseconds. Then we press the start button and we wait 20 milliseconds. And the reset pressed for 5 milliseconds, and we wait another 10 milliseconds. So our expected output for this is we want to count up from 0 to 4, just like we did on the last one. And then we pause for 5 milliseconds at 4. And then we start counting up again until we hit 9. And when we hit 9, the segments are going to stay at 9, and we want to see our LED victory pattern play for the remaining 15 milliseconds there. And then upon hitting reset, we want to see that solid 0 for 5 milliseconds, and then the segments at double 0 for another 10 milliseconds. So let's go ahead and run through this one as well. So we can see we count up to 4 here. That's our first start stop enable. Our value is also being computed correctly here. Forgot to mention that for some of the previous states. For instance, for this one, in target is 10, and for this one we have 9. So we can see we count up, start stop again, so we stop at 4 just like the last one. But this time, instead of hitting reset here, we want to start counting again. And as we can see, we do that. Start stop enable is high, so we're counting. And we can see our LED victory pattern plays there upon reaching the value 9. And then we wait, and it continuously plays for this entire time until, as soon as we hit the reset, everything goes back to that reset state we've been over a couple times with the rightmost LED at 0. And then we, after releasing reset, we can see our anodes are still going at that 1 kilohertz rate, or in this case, I guess it'd be 1 megahertz because we scale time. But we're showing double 0, which is the important part. So our next one starts at 115 milliseconds. That's number 6. And so we set our switches up to 90. We're going to press start, wait 100 milliseconds, press stop, wait 10 milliseconds, press start, and then wait another 10 milliseconds. So the expected output for that would be to go from 0 to 90 in 90 milliseconds, and then 90 on the segments with the victory pattern running for 10 milliseconds. And then we want it to just be 90 with no victory pattern playing because we hit stop. And then 90 and the LED runs victory after another 10 milliseconds, and then 90 again with the LED victory pattern running. So we're basically showing the functionality. We can count up to 90, as well as showing that we can start and restart, or stop and restart our victory pattern by pressing the start stop button twice. So as we can see, we are counting up here. We have a start stop enable. our in count value is properly computed to 90. So from here, I'm just going to zoom out and scroll over some. We can see the tens digit value changing at the same rate, which is a good sign for us. And we can see 40, 41, 42, all the way up until we hit 90 over here. And we see from there our LED pattern begins playing when we hit 90. And we also see it stop 10 milliseconds after, which is good, upon hitting the start stop button. And so we have all zeros, it's blanked. We hit it again and it restarts from the beginning, as we can see. And then we do not hit reset at the end of this one to terminate it, because we're going to look at some higher end cases on the next two. So at 235 milliseconds, 235 is when we start our next state. And that one is we set the switches to a lower value. In this case it's 89, and we're going to wait 15 milliseconds and see what happens. So, and then we're going to set the switches to 99 and wait 10 milliseconds. So we expect that we count upwards because our start stop enable is still high and we're not at the value we need to be at, and we don't expect to see any LED victory pattern. So let's see, and then we'll hit, upon resetting our, it's going to stop at 99 as well. That's something else we expect. And then we set our switches to 99. It should stop at 99 on its own because we have that condition set in. And then as soon as we set our switches to 99, it will start playing the victory pattern because we did attain our value. And as we can see here, our value gets set here to 89. And so our victory pattern stops playing and we begin counting up again, and we hit 99, but you know, it's not programmed for 99, so no victory pattern. Our count is still enabled for the entire time, but we don't go higher than 99, which is a good sign. And then we see a victory pattern play upon hitting that 99 value. Good. Alright, so what's our next case going to be? That's our final one as well. We set our switches to 103. We wait 10 milliseconds and our reset is pressed for 5 milliseconds. And then that's it for the simulation. We expect that our LEDs will be instantly blank so that our victory animation essentially stops playing. And then we're going to stay at 99 because we don't want to count higher than 99 if we can help it. And then we don't see any victory animation. So this basically just shows if the user puts in a value higher than the 99, we're just going to stay at 99, no victory pattern. So we can see that here as well. Right here we have our victory animation stop. Our program value is 103, but no victory animation, no increase from 99. We are constantly 99. And then we hit this reset, which we've been over a couple times. We can see our rightmost anode is on. That's the only one that's on, and they're both at 0. And upon release, everything's at 0. And we can see our count, start, stop, enable, timer mode, LED mode, all of that are gone to 0 upon reset. One more thing I would like to show before I end the simulation part of this video is to just show that refresh rate, to show that we do have our 7-segment display changing which one is on and off, and we'll see that in person as well on the video. But it's always important to check on the simulation before you actually put it into the hardware so you don't run into issues like this. And we can see, you know, we know E is the rightmost, D would be the second one from the right, and F is just blanking all of them because we're not using the other two. So that should do it for the simulation part of this video, and I will see you inside the in-person part of the component. Hi, this is Michael Lozen again, and this is for Lab 3, my partner still being Terrence Hall. So there's my component, there's my face. Alright, so we can show off a couple things of functionality. I'm just going to go ahead and set the value to 4, hit the start button, and we can see it starting to count up. And when we hit 4, there's our LED pattern. It looks a lot better here than it does inside code with just 1s and 0s. And I can hit stop to stop the LED pattern. And I'll hit start and it'll play again. And I'll hit reset. As I hold it, we see a solid 0, which is a lot brighter because it's 100% duty cycle as opposed to the 25% we were having before. Let me just play around with a couple different values. So let's make our count value to 2 here. We see our victory animation flashing. But hey, let's say I want to set it to 6 instead. Oh, alright. Well, we're going to count up to 6. There's our victory animation again. But let's say I want to set it to a lower value. Well, no victory because we're not at the value we programmed it to. And if I hit start again, we count up again. Sorry, I hit stop to stop it, so I can show that again one more time. So let's program it to, let's do 16. And we go up. Let's say we want to do 17. Okay, go up to 17. And now I set it to 1. Oh, so we're going to count up. I'm not going to make you sit through it counting up to all 99 values. I'm just trying to showcase some of the things. But we can see both of the 7 segments work perfectly fine, and we saw that in the simulation as well. I'm going to hit reset here, hold it down, goes back to 00, hit start, victory animation. I think that should cover all the bases. If the simulation didn't cover it, now we can see it in person. It looks cool. All right, thank you.